All right, welcome. I know you guys have been studying black hole properties, and I wanted to just do a quick summary. So if you imagine this circle I've drawn is really a three-dimensional spherical shape, and it's a black hole. Here's what we know. We know that by definition, a black hole is a region in space-time in which nothing can escape. The escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than the speed of light, not even light that would be inside the black hole or could be inside the black hole could ever escape. So since nothing can escape a black hole, then anything inside of it cannot be visible. And if it's not visible, it's black. But it's not a hole. There's a lot of misconceptions. Black holes are the most massive objects that we know of, and all of their mass is confined at the center. And the center is what we call a singularity, which is a point that approaches, theoretically, infinite density. So if you think of a density as mass per unit volume, the volume is smaller and smaller and smaller at the center. So it's a point approaching zero volume with all of its mass. So a black hole will have a lot of empty space surrounding the singularity at the center. And all of the mass is gravitationally compacted and contracted down towards that singularity, which is what we call the center of the black hole, and the region in which the density approaches infinity and the point in which where all the mass resides. But a black hole has a radius. We call it the Schwarzschild radius. And it's the distance from the singularity to some spherical boundary, some edge of the black hole, where the escape velocity at that edge would be the speed of light. So if you're on that edge, that boundary, we say that's where the escape velocity, which I'll abbreviate VESC, is equal to c, the speed of light. If you're inside the event horizon, once you're inside the event horizon, then the escape velocity, by definition, exceeds or is greater than the speed of light. And if you're outside the event horizon, then the escape velocity is less than the speed of light. So you can observe all events outside the event horizon. That's why it's called the event horizon. Events outside of that boundary, that spherical boundary, are observable. They're events that you can witness, but any events inside the event horizon cannot, and they're within the black hole, so you will not see them. So the event horizon is the boundary between what's inside a black hole that you can't observe, what's outside a black hole that you can observe. And the distance from the event horizon to that singularity is called is a radius, and we call it the Schwarzschild radius. And I have a couple problems that we're going to study where you can theoretically imagine any mass to be compacted so small that it could become a black hole, where the escape velocity would be equal to the speed of light. And we're going to see what the radius of that object is. You can theoretically calculate what's the Schwarzschild radius for you, for Earth, for the sun, for any object. And the argument is that the more massive an object, the larger the radius. The less massive, the smaller the radius. Now, in reality, we think that black holes have a minimum mass of about 3 solar masses. So we think you need to have at least 3 times the mass of the sun to create a stellar mass black hole. That is a black hole that's left after a type 2 supernova of a massive star, stars that are greater than 25 solar masses to begin with. Once they end their life and these type 2 supernovae and their cores collapse, they usually have at least a minimum of 3 solar masses. And then they're compacted down to a very, very small radius, which is what we're going to calculate. How big is that radius for a 3 solar mass black hole? Obviously, they can get larger and larger, and there's a supermassive black hole at the center of all galaxies. But how large are they? What's the radius? That's the Schwarzschild radius. How much mass do they have? All that mass is compacted into this tiny little volume, this singularity of space-time at the center. And these are the basic properties of all black holes. So I just want to remind you of some old ideas that we studied. We studied escape velocity in previous units, and this was the formula for the escape velocity, that you could calculate the velocity you need to escape from the surface of any spherical object, any mass of some known radius. So in this case, m represents mass in kilograms. If you know the mass of Earth, you know the radius of Earth, r. Remember, radius in SI units is in meters. Then you can calculate the velocity needed to escape the surface of Earth. We derived this in a previous unit, and letter capital G is the universal gravitational constant from Newton's universal law of gravity. And just a quick reminder to 3 sig figs, that's about 6.67 times 10 to the negative 11th, which is a constant. So as long as you know the mass of the object you want to escape and its radius, you can calculate the velocity needed to escape that surface. Now, if you want to calculate the radius of a black hole, which we call the Schwarzschild radius, all you simply do is substitute c for the escape velocity, because by definition, a black hole has an escape velocity at its event horizon equal to the speed of light, which is how we define the radius. So if you call that c and you set it equal to 2g m over r, and you want to solve this equation for r, the radius, then simply square both sides, and by doing so, solve for r. Rearrange this. The square root cancels, cross multiply it, so you get r on this side equals 2gm over c squared, and you can see how the Schwarzschild radius equation is derived. Very simple, from the escape velocity equation that we've already studied, by just using the speed of light as the escape velocity. So here's my question for you. All right, what would the radius, the Schwarzschild radius, of Earth be and the Sun if it were to be compacted so small it became a black hole? And all you have to know, if you look at this equation, is the mass of the object, because g is a constant, c is the speed of light, which is a constant. Plug in your given constants. The mass of Earth to 2 sig figs is about 6.0 times 10 to the 24th kilograms. Substitute that in, figure out the radius. How big would Earth be if it were compacted so small that at that radius the speed of light would be, the escape velocity would be equal to the speed of light. And then do the same for the Sun, given that the Sun's mass is 2 times 10 to the 30th kilograms. Plug those values in here, calculate the Schwarzschild radius, report your answers in the discussion to 2 sig figs. Good luck.